I am Jose Quevedo, a master's student at the University of Rhode Island. I am here to present our work on selecting between evolutionary and classical algorithms for the CVRP using machine learning. To sum up quickly, this work explores the use of using machine learning for recommending the best heuristics for solving instances of the capacitated vehicle routing problem known as the CVRP. To explain our work, it will be done in 4 parts. First, I'll introduce the CVRP. Next, I'll discuss the algorithm selection problem in respect to the CVRP, followed by the machine learning methods used, and then conclude with our results. The CVRP is a variant of the well-known vehicle routing problem, known as the VRP. The objective of the VRP is to minimize the costs incurred for organizing a fleet of vehicles to service a set of spatially disparate customer demands. CVRP has the additional consideration that the vehicles have some capacity constraint when servicing the demands of the customer nodes. Figure 1 on the poster displays an example of the CVRP instance, which has a single depot in the center and must service 12 customer nodes with 4 vehicles, also called routes. The costs incurred are indicated by the values on the edges. Now, another well-known problem is the algorithm selection problem. The algorithm selection problem is concerned with the selection of the best performing algorithm out of a set of algorithms on new instances of a particular type of problem, in our case, the CVRP. Predicting and applying the best performing heuristics on a given problem instance has potential to reduce computational time and achieving superior solutions as opposed to applying a single heuristic, even if that heuristic is the overall best performing heuristic, often referred to in the literature as the single best solver. The work consisted of a set of 4 heuristics, which were 1, the clock and rate saving algorithm. Standard algorithm for the CVRP, it focuses on finding savings by merging routes. Its recognition is well-deserved, as in our case, it was the single best solver, with just under 50% of the test instances having this as the best solver. Next, sweep algorithm. Here, nodes are sorted by their polar coordinates in ascending order. As the list is traversed, nodes are assigned to a vehicle until its capacity is met, and then a new vehicle is added to continue the process. Next, the accelerated genetic algorithm. This algorithm was implemented entirely on a graphical processing units, or GPUs, due to their ability to parallelize large data sets. The acceleration proved helpful in providing good solutions of good quality in acceptable times. Last was the SelfOrganizing Map for this CVRP. This is a novel algorithm developed by Dr. Steinhaus. It is a neural network based on the elastic band idea, where neurons are ordered on circular bands. These neurons are stretched towards the nodes until they are associated with a single node, and this continues until all nodes are associated with a neuron. The bands represent a route and thus will provide a solution. A problem set of 5,000 CVRP instances were generated and passed on to each algorithm to solve. These test instances were created on the 2-dimensional Euclidean plane. This set was represented by a set of 23 features derived from the literature. These 23 features largely describe the size, spatial attributes, and capacity constraints of each problem instance. Figure 3 displays 5 of these features. Now for the machine learning method to use. Again, each of the 5,000 instances were passed onto the 4 algorithms for each to solve and obtain some cost. For each instance, there was only one algorithm that outperformed the other 3. In the context of supervised machine learning, this was the label for the instance. Therefore, we had an array of 5,000 labels and a matrix of 5,000 by 23 features representing instances, and thereby providing us with data to train our machine learning models. A supervised neural network known as the multi-layer perceptron model was utilized here. This neural network consisted of an input layer receiving the feature values, an output layer providing the predictions, and a number of hidden layers in between the 2 layers that transformed the feature data into predictions. The model was trained and tested with the feature data and labels using an 80-20 split, respectively, and then tuned using 5-fold cross-validation and grid search. The model's performance was measured against the single best solver's performance. Again, with the clock and rate algorithm appearing for 49% of the test instances as their best solver, then this machine learning approach for selecting heuristics will outperform it by correctly assigning 79% of the test instances with their best heuristic, an increase of 30%. To wrap up, matching problem instances to the best performing heuristic has potential to drastically improve solution quality and reduce computational effort. This allows for more computationally demanding algorithms for the CVRP to be developed, where they would be used as necessary, and using less expensive algorithms for the other cases. Thank you for your time.